Hello, let's move on with the second part of the chapter 10. This time talking about free electron diffusion. In here we are going to deduce an expression for the coefficient of this diffusion for a warm plasma. So in a warm plasma we'll consider an isothermal gas. So in this case we have for the state equation, equation of state for pressure will be like this. Okay, so the energy equation will reduce to this state equation, where we have the constant temperature for each species. The plasma will be weakly ionized, and we will have also an isotropic velocity distribution. So since it's isotropic, instead of a pressure tensor, we'll have a scalar pressure for electrons. And also, we'll suppose that initially, we'll suppose that E is equal to B, which is equal to 0. Okay, no electric field, no magnetic field to start. In this case, we will consider that our electron density can be once again written like an average plus a fluctuation, and the fluctuation depends on space and time. The average is constant, and the same for the pressure. In this case, since we're using this state equation, for the pressure we'll also have this. Okay, well, let me just write it straight away in this form. It will be average plus fluctuation times Boltzmann constant and temperature, electron temperature. Now consider the continuity equation for electrons. We have the derivative of density with time plus density times the divergence of U, this continuity equation. Okay, now we don't have a variable average, so the time derivative of m0 is 0, and also we will adopt a linear approximation. The linearized form will neglect this product here of two quantities, and we'll just keep the average times this. So the linearized equation will be this one. So this should be small. We also have the momentum equation. For the momentum equation, let's write like this. And let's include the pressure gradient and just the collisional term. No other forces. And here, after linearizing, also we'll drop this part, keep just the time derivative of this, divide everything by the mass, electron mass, and what else? else? Okay, for the pressure we can use the state equation again, and using this relation we have this. So here's the gradient of pressure. These quantities are constant, so they can be written like here. And we have this for the collisional term, because NE is NO plus this, and this times this is 0. Actually not 0, but we drop it. It's a small quantity. Now we just take the divergence. What is the divergence of 8.5? So the divergence of 8.5 will be, and this is constant, and here we add the divergence. So and from this divergence we'll use 8.3 for, we have here n0 times the divergence of u. We have this quantity in 8.3, and 0 times divergence of u. It's minus the derivative of ne with time. So using using 8.34 n0 divergence of u, we get this. We have used it in both here and also here. That's why this has become the same here. Okay, in both places we used 8.3. Then solving for this, we obtain this form for equation 8.7. Where dE is just kTe over me nu c. So this is the coefficient, the electron free diffusion coefficient. Electron free diffusion coefficient. Okay, so this is almost a diffusion equation. So if you take this part, it's a diffusion equation plus this term. But if you have a high enough frequency of collisions, then you can drop this term. You can conclude this from dimensional analysis, that this term is much smaller than this. So we can drop the last term if this is high. dimensional, this is shown in the book, dimensional analysis, shows that the last term in what, 8.8 can be neglected. In this case, you do have a true diffusion equation. For the electron density, the fluctuation electron density. And okay, we have this one. And another equation we can derive is from equation 8.5. If we take 8.5 and consider stationary solutions of this linearized equation, so we'll drop the time derivative here, then we get, if we consider stationary solutions for 8.5, then we get 8.5 reduces to this equation. I just dropped the time derivative of the electron velocity. Or we can write it like this. We divide by the frequency and write it like this. Where this is this. Is the linearized electron flow. So essentially I'm calling this gamma E, and this is just this part divided by the frequency of collisions, right? So I can use either this form or this form for gamma E. Now this is for no electric and no magnetic fields, right? Yeah, we're considering this. Let's add a constant background magnetic field to see how it differs. So this is going to be electron diffusion with a magnetic field. So we'll suppose that the background field is constant, and also we'll start with stationary solutions. In the equation of motion for the electrons, which is 8.4, linearized. Okay, 8.4 is linearized or not? Let me see. No, it's not linearized. Linearized is 8.5, right? So we will use, yeah, but not really 8.4, because 8.4 does not have magnetic field. So let me start again. So not 8.4. It's the equation of motion. And linearized equation of motion for the electrons. So we will use ME and O. Already dropped the advective term for U here. Now we have the electromagnetic force will be this one. So this is added in this case, but without electric field, but we're keeping the magnetic field. And there is the gradient pressure and the collisional term. Then, well, it's stationary solutions, right? So this is 0, and we have minus E and O U E cross B0 minus KTE over ME. This is from the pressure, using the state equation for pressure, and collisional term. So using this, of course. Also, we have already assumed that the electron density is N0 plus Ne prime. Yeah, that is here. And the gradient of the N0 is 0. So this is the rest, though. Remember. Then we'll solve for N0 UE. Cross B over E nu C minus Boltzmann equation, Boltzmann constant, temperature gradient on this. So we have already called this gamma E, right? Gamma E is this. So we can use gamma E is equal to, well, dE minus dE, because dE is this, right? dE is KTE over ME nu C. So this is dE. We can use it minus dE times the gradient of electron density minus, I'll write it like this. So this is the first part. And here we have N0 times UE again, so we know that this is gamma E. Okay. Now for a particular background field in the Z direction, because that's how we have always used, let's keep it in this way. We have, well, it's be gamma is equal to this minus, here we'll have E B0 over ME, which is the electron cyclotron frequency, right? Then we have B0 times Z. So in this case, we can write gamma E is equal to minus dE, gradient of Ne prime minus cyclotron frequency, electron cyclotron frequency over collisional frequency times gamma E cross Z. And here, just to remember, to remind you, this is E B0 over ME. Sorry, not com is Portuguese. With Now, if you compare 9.2 with 4.15, I think 4.15 is in another file. Where is 4.15? Let me check from the previous video. Yeah, here we have J is equal to sigma E minus this times J cross Z. This is very similar to this one, okay, if you compare it carefully. All right, so especially this part. So comparing 9.2 with 4.15 with J with gamma E. Gamma is actually a vector. I'm not putting the arrow on its top, but it's a vector. Okay, J, gamma E in place of J and sigma in place of dE in place of sigma. I think it's minus sigma, right? Yeah, the first sign is positive, here is negative, so this is minus. In this case, and E is substituted by, well, actually gamma here is a minus, so gamma doesn't have to be negative. It's actually E which is substituted by minus gradient, right? So if you change all these things in analogy with 422, where is 422? I have this for J, and then for J we have 422. Then we can write gamma E is actually minus D, the divergence of this, okay. This you can compare with 422, which is actually J is equal to SE. So in section 4 we had derived this expression going through this equation, and here we're going through this equation to derive this corresponding equation, right, expression for gamma E. In here we have D equal to D perp. This is the diffusion conducting, well, it's in this place it's not conducting, it's diffusion coefficient. D parallel, so the diffusion tensor, this is the free diffusion diet. Equation 9.4. This is 9.3. What are the expressions for these coefficients? We have them. You can check. They are given by this. In the perpendicular direction you have this expression in terms of the electron cyclotron frequency. dH will be also written in terms of the electron cyclotron frequency and the collisional frequency. And dE is the same as D parallel, which is just this. I have not derived this in detail. I'm just giving you the basic flow of the derivation. You can check it, carefully redo it if you want. But since it's very similar to the one we have done in the previous section, so I'm not repeating everything for this case here. So, to obtain the diffusion equation for the electron density with the constant background field, let's take equation 8.3. Let me see, 8.3, where is it? Okay, let's try to start from here, and we'll use, in place of N0 U, I'll write gamma E. So using 8.3 with gamma E. Now using 8.3 with gamma E. We can rewrite 8.3 in this way. I'm using 9.3 for gamma because we had two expressions for gamma E, right? You have also 9.3, which is, no, this is not 9.3. Well, 9.3 is, as I said, it's not this one. 9.3 is actually this one, right? This is 9.3. Okay, so we have gamma E, which is also an EUE. It's also minus d dot gradient of n. And this is what we're going to use here. Using 9.3 for gamma E. The equation becomes del E, del N, del T, divergence of d gradient of NE. Now we can use 9.4. 9.4, these the components for, components for the tensor, for the D tensor, using 9.4 for D. We have this x d del NE del x dh del NE del y minus dh del NE del x plus d perp del NE del y plus z dE del NE del z. If we use 9.10 into 9.9, you can write it using 9.10 and 9.9. You can see that this is actually d perp del 2 del x2 plus del y2 and e perp plus de del 2 and e del z2. Now, this equation is almost the diffusion equation with the, well, it's actually You have here the two components, horizontal components for diffusion, for a Laplacian, which is present in the diffusion equation. It's del t equal to Laplacian of m. In Cartesian coordinates, these are two components of the Laplacian plus this one, right? The difference is that the coefficient for this is different from the diffusion coefficient for the other ones. Okay. Now, if we have both electric field and magnetic field, then we have, and using also this, we're looking for stationary solutions and constant temperature. Yeah, the momentum equation for this case is MEUE, which is gamma E, is equal to ME, capital ME, times the electromagnetic force, which becomes this, minus dE radian of ME. This has just been introduced. This is the flow of electrons produced by the electromagnetic field and the density gradient. And here ME, where ME is equal to minus 1 over NEE. Yes, is that tensor? It's from, if you check the previous video, it's from 4.28. Okay. Now, in the next section, we're going to talk about a very important phenomenon, which is bipolar diffusion. In bipolar diffusion, let's start with equation 8.15. Let me see. 8.15 here. Let's start from this one. From 8.15, we have this equal to minus dE gradient of this, and dE, we know it's this expression. Frequency of collisions of electrons with neutral particles, this is Boltzmann constant. I had previously written nu C, but now I'm using UCE to make it explicit with that the collisions are between electrons and neutral particles. For ions, you have gamma ion equal to minus, the same thing, just change E by I. And you have this. This is the ion-free diffusion coefficient. Well, since both dE, you see it's inversely proportional to ME, right? So here it's inversely proportional to MI. So since dE and dI are inversely proportional to ME and MI respectively, and the mass of electrons is much smaller than the mass of ions, it means that the electrons diffuse much faster than the ions. Then you have this coefficient here is much smaller than the diffusion coefficient of the electrons. Well, in that case, that will leave an excess of positive charges behind. So this will generate an electric field that will accelerate diffusion for ions, and it will slow down diffusion for the electrons. So this is the electric field generated by this charge separation that happens due to the different diffusion velocities. In free diffusion, the effect of the electric field is not taken into account, but in general, it shouldn't be neglected. So from Maxwell's equations, we know that the divergence of the electric field is rho over epsilon naught, and rho, the charge density, is the charge ion density minus electron density over this. So there is an electric field every time you have a difference between the ion density and the electron density. So you have electric field. In dimensional analysis, you can show that for most problems of diffusion in plasmas, the electric field generated by the charges cannot be dropped, cannot be neglected. So diffusion combined with ions and electrons and forced by this electric field of the difference of diffusions is called ambipolar diffusion. So we can say that ambipolar diffusion is caused by the electric field generated the difference in I and E due to different diffusion coefficients. The I, not so much small, but smaller than the E. So let's try to compute the diffusion coefficient for ambipolar diffusion. We start with the charge density for different alpha particles. Usually we are adopting this form. Let's do the same here. And now alpha will be electron and one type of ion. With the fluctuation part much smaller than the average and small, very small. Very small U alpha. So the linearized continuity equation will be this. We have already shown this one. And the linearized momentum equation with a constant temperature and zero magnetic field for B equal to 0. The momentum equation will be this. The linearized momentum equation, we have this for the electric force, the pressure for constant temperature, again the state equation for pressure, and the collisional term. And we know that the electric field should satisfy equation 10.5. Okay. Here we will consider that the collisional frequency between ions and neutral particles is 0. So the plasma is weakly collisional, and the mean velocity of the neutrals is 0 as well. Let's take the divergence of 10.12, and we'll use 10.11 for the divergence of u, because here we'll have the del t of divergence of u. So in place of divergence of u, we'll use minus the del n del t. So this is becoming a second order time derivative with, so this is with 10.11. Then we have this minus q and the divergence of E plus this is the alpha, general expression, the alpha, L alpha, the gradient, divergence of the gradient will be the Laplacian. Then we have the last term, also with the divergence of u becoming the derivative of n. Now, if we use 10.5 for the Maxwell equation for the divergence of E, using 10.5, we have this electron plasma frequency will appear here, and I minus NE plus KDE ME Laplacian of NE prime minus nu CE del NE del T. And this will become minus pi. Now this is for electron, and for the ion we have this. Here the plasma frequency was used, and this was defined in chapter 1 of the book. So its plasma frequency is NE square over LE epsilon square. Electron plasma frequency, this is from actually chapter 2, 2.2.9. Okay. If we have many collisions with neutral particles, then the second derivative with time can be dropped. So if is high, then you can divide all terms by nu CE, and then here we'll have 1 over nu CE, and this will be much 1 over nu CE times this will be a very small term. Okay, if it's high, then can be dropped. Okay, now let's drop these two terms. Use electron plasma frequency similar or the same order of magnitude as the ion plasma frequency. So these two quantities will be approximately the same, and then we sum both equations. So we'll do 10.14 plus 10.15 with this approximately equal to this. Oops, this is ion. And without the second order derivatives, we get TE Laplacian of this plus KTI Laplacian of this minus ME nu CE derivative of this with time minus MI nu CI MI T equal to 0. And we'll do the following approximation: n e prime equal to n I prime. So we'll call them just n. And I approximately the same as n e, which will be, this is for the fluctuation part, just m prime. So we get TE, this is Boltzmann constant, TE plus TI Laplacian minus ME nu CE plus MI nu CI del N del T. Which will lead to this equation. dA times the Laplacian with dA equal to KTE plus TI over ME nu CE plus MI nu CI. And this is the M bipolar diffusion coefficient. Now we can do the same with a little more realistic approximation. So instead of using Ni equal to Ne, we use Ni equal to a constant times Ne. They don't have to be exactly the same, so this is a constant. So in 10.16, if you use this 10.16 here, then we can rewrite this equation like this: KTE plus CTI Laplacian of NE is equal to ME nu CE plus CMI nu CI del NE del T. Or you could just write del n E prime del T equal to this. It's a diffusion equation with dA equal to k Te plus Cti over m E nu Ce plus Cmi nu Ci. That's the new and bipolar diffusion coefficient, and we have and rho is equal to the charge density is just this, which in this approximation would become this, C minus 1. In this case, 10.5, the Maxwell equation, 10.5 becomes divergence of E is equal to E and E prime C minus 1 over epsilon 0. So you see that whenever you have a higher difference between Ni and Ne, then the electric field will become larger, and then and bipolar diffusion will become more important. The final step in this chapter is to talk about diffusion in a fully ionized plasma. In fully ionized plasmas. This is where we do it with MHD equations. Instead of checking alpha species, we're going to do it with single fluid MHD equations, okay? So from the simplified MHD equations from chapter 9, we have this rho m du dt equals J cross B minus gradient of P, the momentum equation. That was 6.6 in chapter 9. If we consider stationary solutions, then we have J cross B equals gradient of pressure. Okay, note that if the electric field is equal to 0, which in this case is what we have because of the charge neutrality, then rho is equal to 0. Okay, since we have charge neutrality, approximation used in MHD equations, the electric field will be 0, and rho, the charge density, is also 0. Now, this is mass density, but the charge density is 0. From equation 6.10 of chapter 9, we have from 9.6.10 without whole term, we have J equals sigma conductivity plus U cross B. So we have seen all those equations, so I'm just repeating them here. This is the longitudinal conductivity. And we'll call this 11.2. If we take 11.2 cross B, we get J cross B is equal to sigma E cross B plus U cross B, right? Which is equal to sigma E cross B minus B square U perp 11.3. Now, why is this equal to this? I'll leave this as an exercise for you to show that this is actually, I have shown some similar cases in this series of videos. So we could just draw a schematic with those vectors, compute those cross products, and see that this is actually equal to this one. I'll leave this as an exercise for you. Now, using 11.1 into 11.3, so where is 11.1? Here. J cross B into J cross B here, we get the gradient of pressure is equal to sigma E cross B minus sigma, no, sorry, this is the absolute value square, U perp, and we can solve for U as E cross B over B square minus gradient of P sigma B square. Now we see here that the perpendicular velocity, it's perpendicular to the magnetic field because of this, and the component of the gradient of pressure as a function of the diffusion coefficient. Now the flow due to the this part, which is called diffusion velocity, the flow due to the diffusion velocity can be computed like this. It's represented by gamma perp, and it's m times U perp, which is minus, I'm just ignoring this part here to check the row of the second part, not considering E cross B drift. This was defined after 8.15, so yeah, m gamma is m times U. For two fluids, this is for image D, one fluid. For two fluids, we have the pressure equal to PE plus PI, which is this for constant temperature. Then 11.5 becomes gamma perp is equal to minus nk. I'll use a state equation for the gradient of pressure here, plus Ti gamma del m, nabla m, sigma B square, which is also written like this. So all I have done is to use 11.6 into 11.5 here, and then we end up with this. Here, the diffusion coefficient is nk Te plus Ti sigma b square. This is called the classical diffusion coefficient for fully ionized plasma. Okay, and I think I'll stop here. If I have done chapter 10 too quickly, then you can write me and with your questions, I'll try to answer them, okay? So, good luck in your final exams and with the final classes with Professor Flavia. See you.